Morning, everyone. Hello, Dr. Ola. My name is Omar Najjar, and I am a master's student at the American University in Cairo here. This is the final semester for me. I'm working on material science point of view and more specifically on the implementation of computer simulation technique to solve a real-world problem. This talk, gamma ray effect on the calcium silicate hydrate, the main binding phase of cement-based material, is my master thesis. I'm working with Dr. Mustafa Youssef as well as Dr. Ghulam. Okay, so first, why we need to understand the effect of gamma ray on calcium silicate hydrate or mainly on cement-based material, because cementitious material has been widely used in many applications where they are exposed to the gamma ray emissions, as in the case of the nuclear reactor concrete contaminant, which is known as the biological shielding layer, as well as the storage of radioactive waste like 137 cesium to cement-based waste form. The present lack of our understanding of the effect of gamma ray on cementitious material is exemplified by some failure occurs at the Crystal River nuclear plant reactor, as we can see here, due to the creepy cracking interaction, as well the collapse of the tunnel containing radioactive waste at Hanford site. Mainly the radioactive waste containing different radionuclide like cesium, strontium, and the actinide series. On the short term, as we can see, cesium and strontium are the main source of the radioactivity and radiotoxicity. For the long term, the actinide like uranium and plutonium became the source of the radioactivity. So at this stage, it's more urgent that we can understand the effect of the cesium and strontium. Cesium by itself decay to a stable barium, but this decay happening that first cesium decay to a metastable barium, 95% of it is by this route. And then the metastable barium will decay to a stable barium via a gamma ray emissions. So the interaction between the gamma ray and the material mainly have three mechanisms. The first one, which is the photoelectric effect, and this mechanism, it's more likely to happen when the energy of the incident photon less than 0.1 MeV. And the second interaction is the Beer production, and this has a threshold to happen, which is 1.022 MeV, which is this equal twice the rest mass of the electron. The third interaction, which is the most important one to us, is the Compton scattering. This one happening when the energy of the incident photon between 0.1 and 1.022 MeV. During Compton scattering, we will have the incident photon interacting with the material, and as a result of this, we will have the scattered photon and the recoil electron. The scattered photon then will interact with the other by the same mechanism until it loses its energy. But the most important case for us is the recoil electron. This recoil electron have a high energy, it's high energetic electron, and by itself, it will be interacting with the other atom in the material. The first interaction is between this electron and the other electrons in the material, which is known as the electronic stopping power. This mechanism is slowing down the electron velocity, but it's not responsible for the damage in the material. The second one, which is the interaction between the electron and the nucleus, which is known as the nuclear stopping power, responsible for the atom displacement from its lattice position. And here we are talking about two charged particles, the electron and the nucleus. As a result of this, the energy transfer will be via Coulomb interaction according to the following equation. From this equation, we can see that the energy transfer will be as of inverse proportional to the mass of the target atom, which means that the lightest atom in the material will receive the highest energy. But still, if the atom receives energy, it does not mean that it will displace from its lattice position, except when it receives an amount of energy higher than the binding energy of the atom in its lattice position. Since we are working on cement, understanding cement-based, which consists of anhydrated cement particle, aluminate, calcium hydroxide, and calcium silicate hydrate gel. CSH is the most important phase. It occupies 60 to 70% of cement-based volume. As well, it is responsible for the strength, mechanical property, and durability of cement-based material. Mainly, it consists of 5 nanometer grain surrounded by water. And here we have the inter and the intralayer space, where the intralayer space consists of sheet of calcium oxide, silicon oxide, separated by interlayer space filled with water, calcium ion, and hydroxyl group. The silicated chain in cement-based material play a vital role in determining its mechanical property and durability. And I here just wanted to explain what is a different type of silicate chain we have. When we have a silicon tetrahedral not attached to anything, it's called Q node. And if attached to another silicon tetrahedral called Q1, and so on and so forth. And we are getting the result of this from the NMR experiment, which given us the ratio of Q1 and Q2 and Q3, and we use this to build our model. Okay, so now we want to understand what is the macro scale effect of gamma ray with cement-based material. We have mainly 4 effects. We have the dislocation, bond breaking, radiolysis of water, and dehydration. The dislocation happening here, we have the molecular scale of the pristine CSH, and as a result of the interaction with photon, we have like this silicon atom will be displaced from its lattice position, which will create a vacancy in this position as well an interstitial in this place. But since calcium silicate hydrate, it's a highly disordered material, this will not really affect the properties of material because it's only increasing the disorder of material. The second interaction, which is the most important one, and especially if we are talking about using cement in concrete for the nuclear reactor. So here we have the pristine molecular scale, and as a result of the interaction with the gamma photon, we will have bond breakage. But this bond breakage then will be followed by the cross-linking of the material, as we can see here. The cross-linking is well known to embrittle the material in and especially for the polymer, which the calcium silicate hydrate, one of them. So why is this important? Because in concrete, which we are used in a nuclear reactor, we have 2 kinds of radiation coming from nuclear reactor. We have the neutron and we have the gamma ray. The neutron is mainly to interact with the aggregate, which will cause a swelling. In fact, it is known to induce volumetric expansion in the aggregate. As a result of this, we need the other component to be able to deform in a specific direction. So if we have the CSH cross-linked, this will embrittle and we will start to see some crack in the material. The third effect is the radiolysis of water, the splitting of water to form different species like molecular species, ionic radical species, and how these species interact with cement matrix. It's very complex, unknown, and still, but in the literature, it has been reported that it has 4 multi-scale effect on the pH, as well in the carbonation of the material and causing some degradation in the mechanical property. The final interaction is the dehydration. This is similar when we are heating the cement, the loss of the water from the interlayer, but it has been observed without increasing in the temperature of the bulk material. So what we are doing in our work is that we are trying to simulate the effect of the gamma ray on calcium silicate hydrate by choosing one of the crystalline analog for cement-based material, which is a tubermarite 14 angstrom. Tubermarite 14 angstrom is a natural mineral found in nature. And the notation here, 14 angstrom, meaning the space between 2 repeated layers of calcium oxide. This is the layer we talk about. And as we said, it consists of interlayer and intralayer space. For the simulation and the force field we are using 3 different simulation technique: the ground canonical Monte Carlo, molecular dynamics, and energy minimization. And everyone has its role in the building or in simulating the radiation event. For the force field, we are using 2 force fields, ReactFF, CSHFF. So the force field, for those who don't work in simulation point of view, it is a set of a mathematical expression and parameter used to represent the interaction between different species. And we are using 2 different force fields because every force field has been fitted and used and developed for a specific calculation. Like ReactFF is capable of capturing the chemical reaction, which is anticipated to happen during gamma radiation. And CSHFF has been well developed for the calculation of elastic constant and mechanical property calculation. And this is why we are using it here. Our procedure consists of simulating 5 cascade in tubermarite 14 angstrom, and every cascade has been simulated for 25 picoseconds. And the time chosen it is proof from the experimental point of view is that the development of the damage is within a few picoseconds. In fact, it is within the first or 2 picoseconds, but here we are extending to the 25 in order to reach a steady state in our model. And then we start to apply compressive strain and calculate the stress strain response of the material. Okay, so what we found here, as I said before, as a result of the equations that the energy will be transferred, hydrogen will receive the highest energy. And here we have the amount of splitted water as a function of the cascade. The general is an increasing on the amount of the hydroxyl group, and especially for the final cascade, we have increasing. And also we can see that we have increase in the number of Q1 silicate chains. This means that the silicate chains start to be breakage from itself and forming a Q1 species. This will not to affect the mechanical property, as we'll see in the next slide. Okay, so here we have the stress strain curve after each cascade. And as we can see, the first four cascades still that the ultimate compressive stress at this place. However, after the hydrogen cascade, where we have a good increasing in the hydroxyl group and the gradation in silicate chain, the ultimate compressive stress reached almost 6 gigapascal, which is almost 20% less than the Bristol model. Here we have the ultimate compressive stress. As we can see, for the first four cascade, we don't have any real change, except in the final cascade, when we have the hydrogen atom is the bullet atom. We have an increasing in the number of hydroxyl group, increasing in the number of Q1, and degradation in the ultimate compressive stress. For the Young modulus, almost we have no variation in the Young modulus, and this is because there is a kind of trade-off between the formation of Q1, the breakage of silicate chain, as well some polymerization of silicate chain in other places to form Q3. Q1 is well known to reduce the Young modulus, and Q3 is to increase the Young modulus. So it's almost constant. Okay, so this result I presented now, it has been presented in the Nuclear Material Conference last October in Belgium. And to be more realistic about simulating the effect of gamma ray on cement-based material, we need to simulate this in a disordered structure, because CSH phase is not a crystalline material, it's a highly disordered structure. As a result of this, we move to the next step, which to simulate the irradiation event in defective model of tubermarite. So what is the difference between the tubermarite 14 angstrom and the defective model of tubermarite 11 angstrom? As we can see here that the silicate chain is connected to each other and have infinite length. It's not like the case of the defective model of tubermarite, where we have some breakage in silicate chain. We are missing some of the silicate chain. How we are building this model? By simply removing some of the silicon tetrahedra according to the silicon NMR experiment. So we are trying to mimic the experiment. So the mainly difference here, we have infinite silicate chain made of Q2 only, and here we have finite silicate chain made of Q1, Q2, and in some cases it made of Q3 also. Here we have a calcium silicon ratio 1.7, as well we build a model with 1.5 and 1.3, and here it's a low calcium silicon ratio 0.83, and this model, it's more representative for the new type of cement, green cement. Okay. So now we build our model, and we should to characterize our model in order to understand if it is a good model or not. And we are doing this by comparing some of the results with the experiment. And one of the most important is the radial distribution function, which radial distribution function telling us about the local density of each atom. So if I am a calcium atom, how many oxygen atom around me at a specific distance? And here we have the result for from the experiment and from also our work. Almost we have a very good agreement, except for the silicon oxide. You can see the difference between 3.15 and 3.44. And for some species, we have total agreement between the experiment and our model, from like the silicon 3.15 and 3.15. One of the, I think it's a good characteristic of our model that it succeeds in calculate the coordination number for the calcium oxide 7, and this was one of the points has been used to criticize the model built by computational work, because it always predict a calcium oxide coordination number less than 6 or 5, and in some cases it's 4. However, from experiment we know that this number is 7 and above. Here we have the three models. This is the three model we built: 1.3 calcium silicon ratio, 1.5, and 1.7. If you see the 1.5 model, you can see that it has some kind of a disorder and still have some order. Less than 1.5, we have also the order is well defined. However, after 1.5 for the 1.7, almost we have a very disorder as well. We have a 3D structure for the silicate chain. In fact, 1.7 is more likely that we enter a glassy structure more than a disorder material. We here change just the number of the cascade we are simulating. We are simulating 20 cascade in each model, and then we start to characterize the model. So the development of the cascade, here we have the calcium silicon ratio 1.3. Here we have before irradiation, this is a pristine model, and this is after irradiation. We can see that there is an increasing of the material disorder. This also the same trend for the calcium silicon ratio 1.5. However, for the calcium silicon ratio 1.7, it's totally start to become disorder material. Okay. So our results here, it's regarding the silicate chain and the hydroxyl group, how the gamma ray affects the formation of the hydroxyl group and also the connectivity of the silicate chain. What we can see here from the calcium silicon ratio, okay, sorry, 1.3, 1.5, and 1.7. For 1.3 model, we have a fluctuation on the formation of the hydroxyl group, and the general trend is to increase the amount of the hydroxyl group. In the same fluctuation, if we look at the silicate chain, we have also the formation of Q0 and Q1, and this is well known to cause a degradation in the mechanical property of material. The same trend has been observed for the calcium silicon ratio 1.5, the fluctuation on the hydroxyl group, and the increasing in the Q0 in the silicate chain. For the calcium silicon ratio 1.7, we don't have almost any fluctuation on, okay, just, yes. Okay, so for the calcium silicon ratio 1.7, we have almost a constant number of hydroxyl group, and this has correlated for the silicate chain where we have the same trend. It's a constant number of silicate chain. We don't have a breakage in the silicate chain, and it is proof in which I will explain in the next slide. So here we can see that the hydroxyl group has some kind of correlation with the silicate chain. It's not working.
You can put it in second screen.
Click on the small one on the bar.
Okay.
No, yeah.
But you can put it in second screen as well.
Okay. So how the hydroxyl group affect the silicate chain? Okay. Okay. Just let me. Okay. So why the hydroxyl group affect the silicate chain? In fact, the answer for this question coming from a more accurate simulation technique from a first principle calculation, density function theory, and this work is done by Dr. Omar, doping as a way to protect silicate chain in calcium silicate hydrate. So, as it has been mentioned in this paper, that the breakage of silicate chain is a two-step process. It starts by the hydroxylation of the two silicon tetrahedra. And after that, after we have the hydroxylation, we have the bond breaking. And this in good agreement what we have in our result, where we have an increasing in the amount of the hydroxyl group, we start to see a breakage in the silicate chain. Okay. So our conclusion. An increasing trend in the model degree of disorder has been observed in the 3 model. The model with a high calcium to silicon ratio, the calcium silicon ratio 1.7, shows stability in the amount of the hydroxyl group as well as the connectivity of the silicate chain. In fact, this is in qualitative agreement with the experiment, because we know from the material used to resist radiation that the amorphous material, it's more radiation resistant than the crystalline material. And okay, so the hydroxylation of silicate chain is the first step for the development of the irradiation damage. Thus, by blocking the hydroxylation, we can protect the silicate chain. It has been reported in the literature that we can blocking the hydroxylation of silicate chain by doping the silicate chain specific element like phosphorus and aluminum. Okay, thank you. Thank you.
Thank you. So do we have questions for Omar? You have? Yeah.
Yes, a technical one for the real thing. What is the depth of irradiation in a real reactor? Like like I come from a very nuclear country. We have very old nuclear plants, like 40 years. What is the depth of the irradiation inside the reactor? Is it like 1 centimeter, 10 centimeters? What is it? Yeah. Well, the damage. Well, how much? What depth you see the damage inside the concrete? Because you were showing some cracks. The first picture, you were showing some cracks. Which one? The first picture you were showing.
Yeah. Okay.
Yeah, the experimental picture. Yeah, the cracks. Yes, exactly.
They have a very small crack. They found some crack, and after that, whenever they try to remove this crack, start with the whole reactor. So yeah, at the end, they will shut down the reactor because it cannot repeat.
Okay.
Do we have other questions? I have a question. When you do your cascade degradation simulations, you use a hydrogen atom, right, to make the energy of the element, to have a bullet in your system, right? This hydrogen atom can react also with the rest of the system. Your hydrogen atom, they can react with the system when the one you had.
Yeah.
Yes.
Yes. But to be honest with you, I think that the reaction has some kind of penalty for the formation of the hydrogen molecules you are asking about.
H2, yeah.
Yes, I think there's a penalty for this because I did not observe any hydrogen molecule during the radiation, and this is something. It's not because from experiment you know that we have hydrolysis formation which and should have not been observed.
Which it depends maybe on which reacts you are using. So because there are different parameters. So.
Using the
yes.
calcium side, and for the calcium.
Okay.